The hydrogen in the carboxylic acid is a strong acidic hydrogen. So whether the base is a strong base or whether it is a weaker base, that base can come and take that strong acidic hydrogen to get the conjugate base. For example, ammonia or sodium carbonate or sodium bicarbonate, all of those are weak bases, but the reaction can happen. Ammonia, in this case, is going to act as a base, and since it acts as a base, the reaction is going to be an acid-base reaction. So the lone pairs on the ammonia are going to come, they're going to take that acidic hydrogen, form a negative charge on the oxygen. And you're going to get, in this case, the ammonium. Ammonium is a term that we use whenever the nitrogen is a positive charge. It's going to be ammonium and it's going to be benzoate. About the effect of electron withdrawing groups on the acidity of the hydrogen. And we said that if you have an acidic hydrogen and next to that acidic hydrogen there is an electron withdrawing group, then that electron withdrawing group is going to take electrons away from the hydrogen and leave it partial positive. The more electron withdrawing groups are there around the hydrogen, the more partial positive the hydrogen is. And the more partial positive the hydrogen is, the more acidic it is. So for a hydrogen to be acidic, you want it to be present next to an electron withdrawing group. The more, the better. Electron donating groups, on the other end, they donate electrons to the hydrogen. So they decrease the acidity of the hydrogen because the hydrogen will no longer be partial positive. So the more electron donating groups, the more basic the compound is, the less acidic is the hydrogen. So let's have an example over here. Which one is more acidic? First of all, highlight your acidic hydrogen. Okay, this is going to be your acidic hydrogen. All of them have benzene, so pass over that and look at the electron withdrawing groups. The more, the better. So this one is going to be the most acidic, then this one is going to be the least acidic in there. Electron donating group, they decrease the acidity. This is an electron donating group on the para position. This decreases the acidity of this acidic hydrogen in there, compared to an electron withdrawing group that increases the acidity. This is a moderate donating group, so it's going to be in the middle. The closer the halogen is to the carboxylic acid, so over here, this is very close to the carboxylic acid in there, that is going to make this hydrogen more acidic because it's going to take electrons away from the hydrogen and it's withdrawing electrons by inductive effect, meaning that it's taking electrons through the sigma bond in there and leaving the hydrogen partial positive. Same idea over here. You have an electron donating group. This is a withdrawing group in there. Now, for this one over here, this donates electrons by resonance. If it gives electrons by resonance, if I'm comparing between this group and this group, this takes electrons away from the hydrogen, making it more partial positive. This one is giving electrons by resonance in there. So it's still an electron withdrawing group because it's a carbonyl over here. This is partial positive, but it donates electrons as well. So if I want to compare between those two, definitely this one is going to be more electron withdrawing group, so it's going to make this hydrogen more acidic. An alpha hydrogen between two carbonyls can vary in acidity depending on the type of carbonyls that it is connected to. So the alpha hydrogen between two carbonyls is going to be the most acidic compared to an alpha hydrogen between two esters. In order to know or to check the acidity, change the acid into its conjugate base and see if the conjugate base is stable. The conjugate base of the alpha hydrogen between the two esters is going to be the least stable because of the presence of the two oxygens that can donate electrons by resonance, decreasing the stability of the resonance structure in there. Here I do have one oxygen that can donate electrons by resonance to the negative charge, decreasing again the stability. And this explains why the pKa here is less. Here I don't have any electron donating group. So no group to donate electrons. So that is going to make a stable conjugate base. This means that if I have a base around any of these alpha hydrogens, then the first thing that the base is going to prefer to take is the most acidic alpha hydrogen. So the base is going to come and take this alpha hydrogen between the carbonyls of the ketone. This pKa table for the different alpha hydrogens is posted on eCampus. You can bring this table to the exam as well.